Welcome back. Now we'll start in a few minutes the second part of today's training. But before starting with the new exercise, I saw that Ryan raised one problem in the chat. He had a problem in making the interpolation of the cross section. So let's see briefly again how to do this procedure. So this is the problem, how to get the correct interpolation of this cross section. So let me go back to the project. Now I try to explain again how to do this. So I still have the project open. I just go to the geometry data editor. And from the tools menu, I go to cross-section interpolation and between two cross-section. So that's the menu we were looking at. The problem of the cross-section interpolated was here between the cross-section 10 and 11. What you have to do in order to obtain this more appropriate interpolation is to delete the existing one, which were not correct in your case. And you confirm you can hear me, right? Because I have some problem with my microphone sometimes, but now it's okay, right?
Yes, you're audible.
Okay, thank you. And is it Ryan here listening? Because I try to help you with the question you raised in the chat.
I don't know if it's only me. I think your screen is not visible in my side.
Is not visible?
Yeah, I'm not seeing. I don't know if it's only me.
Okay, I try to stop the sharing and start it again. Maybe the problem will fix for you and maybe also for the other. Okay,
Yeah,
can you
okay
now
now.
see my screen?
Okay now.
Okay, perfect, thank you. So we're trying to explain again how to obtain the interpolation of the cross section. Can Ryan confirm he is listening now? Okay, thank you. So I go on in repeating. Otherwise, I would have explained later when you were available. Okay, so now you are here, and here you find a problem. You have first to delete the existing interpolation with this button, and you will obtain this situation. So you just saw the two cross section. And now what you should do is select this button, the first button here. And this tool allows you to draw some chord lines in order to connect similar points between the two consecutive cross sections. And then the interpolation will be forced to follow these chord lines. So you should connect points that must be connected from the upstream cross-section to the downstream. So in this case, the best option is to draw 4 chord lines which connect the two bottom points and the two top points of these vertical obstacles that are located both in the upstream cross-section and both in the downstream cross-section. So when you click on this button, your mouse will turn into this pencil icon, and when you are like this, you can click starting from the point you want to connect, and you have to click the mouse and drag until to reach the second point you want to connect. Once you are above the point, just release the mouse and you obtain this chord line drawn in your window. You have to be quite precise in selecting the points, because maybe if you release here, the chord does not appear. So just have a little bit of patience and try to connect properly 2 points, 2 existing points. And you should do something like this, drawing the 4 chord lines, 2 at the bottom and 2 at the top. You can also draw in this direction, it's the same actually. And once you have these 4 chord lines ready, you can set here the maximum distance again, which was 50 meters. And just by clicking the button Interpolate a new cross-section, you will obtain this new free cross-section, which follow exactly the chord we draw. I hope that now the process is more clear. Okay, yeah, the recording will be available. Yeah, today in the afternoon I will prepare the file and I will put in a shared folder like I did yesterday. And so yeah, you will find all the recording of both the session of today and yesterday. So if you missed some part or something was not clear, you can listen again at the recording for sure. Yes. Okay, so this was the procedure to do to obtain the interpolated cross-section. I hope, Ryan, that now it is clear and you managed to obtain the proper interpolation. Okay, if you still have any problems, maybe you can let me know later and we will go back to this maybe at the end of the session. Or let me. Okay, now it's clear. Perfect. I'm glad it's okay now. Okay, so let's try to move on the last topic of training, which is how to perform an unsteady flow simulation, which is the most interesting part of the RAS program, but it's also the most complex, let's say, because there are more variables, more options, and it's a little bit more complex. But I will try to explain the most important step and the necessary information you need to set in the model in order to perform this kind of simulation. We are going to do this with the exercise 4. You will find the material of this exercise in the training material folder under the folder exercise 4. And we will work on this. In this exercise, the main steps that we are going to do is to open the project that I prepared in the folder, then set the HTAL parameters that I'm going to explain you what are and what do they need for. Then we are going to create the unsteady flow file with the boundary condition and the initial conditions. So we are going to see which are the differences from the unsteady flow and the steady flow information that you need to insert in the schematization. Once you have set the boundary condition and the initial condition, as also we have done for the steady flow analysis, we can create a plan and then perform the unsteady flow simulations and check the results. So let's open the project. I will do now with you. I still have my HEC RAS session open. I just save the previous project and I open this new one. From the file menu, you can go to open and then look for the directory where you save the folder called exercise 3. Go to the folder exercise. Also here I prepared the solution. Then here there is the final project, but let's start from the beginning and try to do together now. So in the exercise folder, no, sorry, this one is the number 3. Now it's the number 4, sorry. But the same in the exercise folder, you will find this project called Dindir. Select this one and open it. Okay, in this project there is a geometry already prepared, and this is a schematization of the upper part of Dindir River located in the Blue Nile subbasin. So we are going to see a little analysis of this part of the Dindir River. Let's have a look to this geometry. Just open the geometric data editor. Okay, in this case, we see the river, the ridge section. In this case, they are more than 160. You can also upload the background, because in this project there is a terrain loaded in the project. So if you go to this option, the background button, you can check the option plot terrain. If you do this, you will be able to see the river located inside this terrain background DTM, just uploaded in the RAS mapper, as we saw also yesterday. The procedure is the same. Okay, let's have a brief look to the cross-section. If you open the cross-section editor, you will see you can move through the different sections and see their shape. You can see each cross-section has been well prepared. There are the main channel and the bank station already set. There is the roughness coefficient selected for the whole parts of the river, and the downstream reach length is constant for all the cross section. They are 500 meters per each other with a constant distance. And here you can see the river follow exactly the path the DTM. It's a quite good schematization of the real path. Okay, now let's move to the RAS mapper interface. So close the geometric data and open the RAS mapper, which can be opened from the main menu, selecting this button. Okay, here, as you can see, there is the DTM already uploaded. I want you to upload another layer, which is a shapefile that contains the hydrologic catchment which this river belongs to. Just to show you that in the RAS mapper, you can see, edit and modify all the layers related to the RAS program, but you can also manage other external layers, such a shapefile. To do this, you have to select Map Layers, then right-click, Reference Layer, Add Reference Layer. This will open a menu from which you can select a shapefile to be uploaded in the RAS mapper. You have to look for the directory where you save the exercise. Actually, the project is saved in the project is saved in the folder exercise, so it should automatically open the path inside this folder. Then you have to select a folder called shape, SHP, and here you can find this file named upper Dindir catchment. Select it, and you see that this polygon appear in your RAS mapper window. This is the hydrological basin that has been used in the hydrologic model performed with the HMS. I know that you have already followed the training online of the HMS software, and so I thought it was nice to show you how the HMS model and the HEC RAS model can be connected together. Because in this case, this is the catchment in which with the hydrologic model, HMS, was computed the drainage flow in this area. You see, this catchment is closed here at the end of our river, and as you can imagine, the portion of area comprising in this most upper part, this area, which is more or less 1/3 of the total catchment, will be drained, and the flow will go directly here at the beginning, at the upstream cross section of our river, while the other flow drained by the rest of the catchment will go inside our river in a distributed way all along the river. So we want to use the flow data, the output of the HMS hydrologic model, as an input for this hydraulic model. And the output from HMS is the flow hydrograph of this catchment. And so we want to use that flow hydrograph as an input for our hydraulic simulation, just splitting the total flow hydrograph in the way I just described. So one part will be used as a boundary condition as a flow which is directly emitted in our system from the upstream cross-section, while the remaining parts of the flow hydrograph will be distributed along the river. Okay, did you manage to upload this layer in the RAS mapper? This is quite useful because the RAS mapper can somehow work like a QGIS, so you can manage and use and visualize different shape file, which is really useful in some cases. So like this, you have an immediately clear vision of how the catchment is and how the river is located inside this catchment. And there are also, if you double click on this layer in visualization and information, you can somehow change, for example, the line, the fill. There are some options to customize, let's say, the layer that you upload. Yeah, for now, it's just okay to see the basin like this. Okay, I talked about the HMS output, which is the flow hydrograph, and you can also see which are these flow hydrograph in the folder exercise. In fact, you can find also a DSS file. If you open it, you see there is one path name, and if you try to plot it, it's the flow hydrograph of more or less 50 years simulated with HMS. For example, you can try to zoom and see that there is a flood event almost every year between generally the month of July and September. And we want to try to simulate also, to do an hydraulic simulation of one of these events. So we are going to use this information, this flow information, as the input in the boundary condition of the hydraulic model. Let's close it for now. Okay, before preparing our boundary condition file, you need to know something about the HTAB parameters. You can find this option in the geometry viewer. Here, there is a button called HTAB tab. And if you open it, you will have this table for each cross section. You see here we are looking at the river Dindir and the ridge called Upper Dindir, and we have a list of all the cross section that are present in this ridge. And for each of these cross section, you see there are some parameters here in the column. There is a starting elevation, the increment, the number of points, and here in the graph, you can see there is some line draws for each cross section. I will try to explain what these grids are, because essentially, when you perform the unsteady flow calculation before of the effective computation, there is a geometric preprocessor that is used to process the geometric data into a series of hydraulic properties like rating curves, curves and family of rating curves. And this is done for all the elements of the geometry in order to speed up the unsteady flow calculation. So when the unsteady flow calculation starts, all these data and tables are already prepared, and so the calculation will be faster. In the specific case of the cross-section, each cross-section is processed into tables of elevation versus other hydraulic properties like areas, conveyance, and storage. And the user is required to set an interval to be used for spacing the points in the construction of these tables. So for example, now the tables that are being automatically generated cover only this portion of this interval of water surface, and these don't seem to be enough. The interval it's identified with the increment, so the distance between each value considered in the table and the points, the number of points computed. The interval is really important because it defines the limits of the table that is built for each cross-section. And you must keep in mind that on one end, the interval must be large enough to cover all the range of stages that may be occurred during an unsteady flow simulation. So for example, if now we compute an unsteady flow simulation and the water surface in this cross-section, for example, will be like this, the tables aren't enough because they do not cover an interval of stages until here, for example. So we must increase the number of points and maybe also the increment time step. But keep in mind that if the interval is too large, the tables will not have enough details accuracy to be good in the identifying changes in area, storage, and so on. And if the computed water surface goes above the table, it can be a problem because the properties are then linearly extrapolated, and the extrapolation can often cause the model to be unstable. So you may get an error in the simulation and the computation stop. So in this case, let's try to fix this in order to prevent our simulation to fail. So we have to change the increment and the number of points from this window. I just want to repeat that this window can be opened from the geometry data editor by clicking this button, HTAB parameter, and from this window you can select the cell increment. This will automatically select all the column, and you can change the value of the whole column at the same time by clicking the button set values. In this case, let's try to use an increment of 0.2 meters. So each properties for the cross section will be computed every 20 centimeters. Let's confirm, and you see that now the whole column has a value of 0.2. Let's change also the number of points. You see now the grid have a higher distance. Each line is more distance one from the other, but they still do not cover maybe enough of the cross section. So let's increase the number of points. So click on the cell points. The whole column will be selected, and by using the option set values, enter a number of 50. Confirm, and now you see that all the cross section have a grid with a space interval in the elevation quite large. That should be enough for the simulation. Last thing we can do to assure our simulation will be fine is also to change the starting elevation, which is the minimum elevation that cross-section will have at the starting simulation, and it must be equal or higher than the minimum elevation of the cross-section. To be sure this is okay, select the column starting elevation and click the button copy invert. So if any of this value was lower than the invert elevation of each cross section, it would be fixed and substitute with the invert elevation of its cross section. Okay, if you have done this, now for the h-tab parameter should be okay for computing simulation. So you should have a 0.2 value for all the column increment and a 50 value for all column of points. Let me see if there are any issues. Okay, it seems to be okay. So let's confirm and save the geometry from the file menu, save geometry. So we are sure that these changes will be saved in our geometry. So now the geometry is ready. We have all the information we need to perform a unsteady flow simulation. Now we have to move and create the unsteady flow simulation file, which contains the boundary condition and the initial condition. The user is required to enter boundary condition at all of the external boundaries of the system for sure. Then it's optional, but the boundary condition can be set also at any desired internal location. And as well as boundary condition, also the initial condition are needed. The user must enter an initial flow at the beginning of the simulation, so the program can compute the initial flow and stage for each cross section, and then it will be able to start the computation. Okay, in the first session of today, we see how to create the steady flow file. In this case, we are going to see how to create the unsteady flow file, which is a little bit more complex, and let's see which are the differences. To open the unsteady flow file, you have to select this button, and this window will open. This is the window from which you can set all the boundary condition, the internal condition, and the initial condition. So everything you need to set to perform an unsteady flow simulation. You see that river, ridge, and river station location are automatically entered here in the box below. These two cross-sections are the external bounds of the system. So this one is the most upstream cross-section where a boundary condition is needed, and this one is the most downstream cross-section that will need as well a boundary condition. If you want to add other internal condition, there is this button add RS that allow the user to add any other cross-section in which you can put some boundary conditions. The boundary condition types you can enter are different types and are all shown here in the top part of this window. There are many, much more than the steady flow analysis. And now we try to explain in a very fast way without going too much in the hydraulic details which are these condition type. And just know that when you select a cell, only some of these types are available. For example, if I select the upstream cross-section, you see there are these 3 options available, while if I click on the downstream cross-section, 2 more condition types are available. So, for example, the most common boundary condition upstream is the flow hydrograph. In this case, the user must insert how the flow changes during the time, and this flowing hydrograph will be applied to the cross-section selected. The stage hydrograph is similar. In this case, you have to provide the software the variation of the stage in time, not the flow. While the stage flow hydrograph is a combination of both the 2 variables. In this case, stage and flow can be used together as either an upstream or a downstream boundary condition. It's a mixed boundary condition where the stage hydrograph will be used for the program until it runs out of data, and at this point the program will automatically switching to use the flow hydrograph as a boundary condition. Then another option that can be used downstream is the rating curve. In this case, it's a single valued relationship that the user must know and insert, while the normal depth is similar to the one so for the steady flow case, in which the user can insert the slope of the channel, the average slope of the channel near to the cross-section location, and this will be used from the RAS processor as a boundary condition. Okay, let's try to insert the boundary condition. So let's start from the upstream cross-section, which is this one. You can recognize it's the upstream cross-section because if you remember, the river stationing is increasing from downstream to upstream. So the higher number will be for sure located more upstream than this one. So let's select the upstream cross-section. For this one, we want to use as a boundary condition, as an input for the simulation, the flow hydrograph we got from the hydrologic model of HMS. So we want to use the flow hydrograph that I show you from the DSS file. To do this, select this cell and click on flow hydrograph. This window will open, and from here you can set all the options needed to insert the boundary condition. There are 2 options of entering a flow hydrograph. You can enter the hydrograph with a table. In this case, you have to select this option. You should set a data time interval, which is a regular time series data. In this way, the program will automatically compute the date and the simulation time, and you just have to write here in the table the flow values along the time of the simulations. This is one option. Another option is to read the data directly from a DSS file. In this case, you have to select from here at the top the option read from DSS before simulation. And you should, we are going to use this option, so select this one. And then clicking from select the DSS file and path, you can choose the file to be read before the simulation. Just click on it, and from here, you can select the file. To do this, you have first to insert in the file list the DSS file you want. So using this button, the Add DSS file, go and search in the folder exercise the DSS file called flow HMS, select it. Okay, so you see here, there is now there is the file name, and here at the bottom you will see all the path names that are present inside the DSS file. In this case, we have only one, so just select this. It's the one, check if the file is the correct one. In the part B, you have BN, which stands for Blue Nile, Upper Dindir, and click OK. Okay, let me know if you had any problems in selecting the DSS file as a boundary condition, or if you managed to correctly select this option. Okay, if everything is okay, we just need to add another couple of parameters in this flow hydrograph editor, which is the multiplier. At the bottom, there are these two options, minimum flow and multiplier. In the multiplier cell, just put 0.33, which is we are saying that only 0.33, so 33% of the flow hydrograph that we select will be used as a flow in the boundary condition, because as I said you before, we are assuming that the flow drainage by this catchment is split into two parts. The 1/3, so 0.33, which is more or less the area of this upper part of the basin, will be drained and go directly in our river through the cross-section upstream, while the remaining parts of the flow hydrograph will be distributed along the river. So we set this multiplier to do this.
Am I listening?
Yeah, there are any questions? I hear someone speaking. Do you have any questions? Check. Only 5. Okay, I do not say nothing, so let's go on. Last thing, we set the minimum flow to be 20. This is just because a flow which is too low can get the simulation unstable. So we set a minimum flow that we know it's okay in order not to get some unstable solution during the simulation. Okay, so if you correctly select the DSS file here at the top part of the window, and then if you set these two parameters at the bottom, you can confirm by clicking OK. And we can go on adding the other boundary conditions. As we said, we want to distribute another portion of the flow hydrograph along the river. To do this, we have to add a cross-section because now there are visible only the most upstream and the most downstream cross-section. We want to add another cross-section, so click on the button Add River Station. And from here, you can see the list of all the cross-section in our river. Let's select the second one. We cannot select the first one because you cannot put more than one boundary condition at the same location. And since this one is the cross-section where we just put the flow hydrograph as a boundary condition, we cannot put another one. So let's select the second one, double click or click on the arrow, and this cross-section will move to the select location list and click OK. In this cross-section, we can enter another boundary condition type, which is the uniform lateral inflow. This option is used as an internal boundary condition, and this option allows the user to use a flow hydrograph and distribute it uniformly along the river ridge, starting from this cross-section to another one, which can be specified by the user. So select the cell of this new cross-section, click on Uniform Lateral Inflow, and the first thing we have to set is the cross-section until which the flow hydrograph will be distributed. Move with the drop-down menu until the second last cross-section, because also in this case, the last one will be the cross-section where we are going to put the boundary condition, because it is the external bound of the system, and we are already set a boundary condition for this one. So let's select the second last, because we cannot have more than one boundary condition at the same time. In this way, the flow hydrograph we are going to use will be distributed from the second cross-section until the second last, so along most of our reach length. In this case, we choose the same option as before, so we want to read the flow hydrograph. So as we did before, select the option Read from DSS before simulation, and then select the DSS file like before. Now it's already visible here in the list of the file. You can just select again this file named BN upper indir and confirm. In this case, in the multiplier parameters, let's put 0.77, which represents the remaining part of the flow hydrograph. We put 0.33 as a boundary condition upstream, and so now we are using the remaining 0.67 part as an internal condition and distributed along the river. So click OK. Is everything okay? Did you manage to insert this internal boundary condition? Let me see if there is any feedback in the chat. Okay, if I do not see nothing, I will assume you are okay and you correctly managed to insert this boundary condition. And so we can go on and set the last boundary condition we need, which is the boundary condition here at the downstream cross-section. In this case, in the downstream boundary condition, I want to set the normal depth as a boundary condition. So as I said, the normal depth is usually approximated with the average slope of the ridge in the vicinity of this cross section. To see which is the average slope, you can go from the main menu and open the profile of the river using the view profile button. You can like zoom in a little bit in the final part of our river, and with the control button of the keyboard you can draw a line and see more or less which is the average, which is visible here, the ratio between delta y and delta x, which is more or less 0.001. So 0.1% is the average slope. So let's copy this value and use it as a boundary condition when you select normal depth. So the friction slope, I just copy the value, or otherwise 0.001 is enough. Click OK, and now this unsteady flow data file is okay and is ready. It has been filled with all the necessary information to compute an unsteady flow analysis. So let's save this file. From the File menu, select Save As, and just save it like unsteady. See? Confirm. Okay, and now our file has been saved. We have inserted all we need about the boundary condition, but we still miss the initial conditions, which are mandatory to perform the unsteady flow analysis. Is everything okay? You need a bit of time to set this boundary condition, or have you already done it? Okay, everything seems to be okay for you. So let's see the initial condition. You can look at the initial condition just selecting the initial condition tab located here at the top of the unsteady flow data editor. And this is the window where you can insert the initial condition. The model need some initial condition to be set for the system at the beginning of the unsteady flow simulation. This condition must be determined in terms of flow and stage information for each cross-section. And the most common method to insert this initial condition is to enter a flow data for every reach in the river system, and then the program will automatically compute a steady flow analysis in order to perform a profile and so to obtain all the stages and the flow at every cross sections. So you need to enter an initial condition, an initial flow, here in this case. User specified fixed flow. We only have one reach. If we had multiple reach, you should enter multiple initial flow, one for each reach. Let's set 100 cubic meter per second as initial flow and save again the file with this new information we have set. Okay, now the unsteady flow data is ready. We have set the boundary condition, internal condition, and also the initial condition. So last thing we have to do to perform the unsteady flow analysis is to create a plan. To do this, go to the main window and select the unsteady flow analysis button, which is this one also highlighted in the slide. When you click this button, you will see the unsteady flow analysis editor. And from here, we have to insert all the data and the option necessary to perform a simulation. From here, we will create the plan file, which essentially is the file that defines which geometry and which unsteady flow data are to be used. The plan is also provide a description and an identifier for the run, and then from the plan we can set all the options that define our simulation. So let's start to analyze one by one all these options that must be entered in the plan file. First of all, you have to select which geometry file and which unsteady flow file you want to use to perform the simulation. If you have multiple geometry file and multiple unsteady flow file, from here you can select which one you want to use. In this case, the correct ones are automatically selected because we have only one. Then the second section you can see in the plan editor is this one, the programs to run. Here you can check the box of which program you want to run during the computation. The first one is the geometry preprocessor. I mentioned it just before when I said that this geometry preprocessor process all the geometric data into a series of hydraulic property tables, rating curves, and all the format that will be needed for the real computation that will be done later. Check this one because it's important for the simulation. And the unsteady flow simulation programs is the real computation. It perform the unsteady flow calculation. Then the post-processor is very important too, because with this program you can compute the hydraulic output variables that are not computed automatically by the unsteady flow computational engine. So essentially, if you check this program, then you will be able to see more detailed output results, which are really important to understand if the simulation is okay and to have more output data that can be used in your study. So make sure you check these three programs: the geometry preprocessor, the unsteady flow simulation, and the post-processor. I just check the chat sometimes because not always I see the notification from while I'm sharing my screen. Okay, let's now move to this other section, the simulation time window. From here, the user is required to enter a time window that define the start and the end of the simulation period. You can simulate a period, let's say, as long as you want. It can be some days, some weeks, some months, depending on also the data, the boundary condition you fix. For example, we use the TSS file flow hydrograph, which covered almost 50 years. So potentially we can also compute 50 years of simulation. This will be quite complex. Let's say we are going to simulate only the hydraulic event during 1 year. I choose, for example, the year of 2003, just as an example. And so here we have to set the starting date, the starting time, as well as the ending date and the ending time. About the date must have 4 digits here. So you must write the date like 2 characters for the day. Let's say 01, 3 digits for the month. You have to use the first 3 letters of the month. So if we want to perform a simulation that starts the 1st June of 2003, we have to write 01 June and then 4 digits for the year, 2003. The starting time will be 00.00, while the ending time will be the 31st of July of the same year, 2003. And the ending time will be 2400. So we are actually going to perform a 2-month simulation. Now, an important thing is that in order to perform the unsteady flow simulation, the Windows data setting of your machine must be changed to the English format. So to make sure this option is set in your PC, in your machine, let's do this check. From the start button, you look for control panel, and from here, oh, okay, sorry, my machine is set in Italian, but you have to look for the option region format, geographic format. And if you select this option, then you should select as a geographic area format. You should check is set in English USA. This is really important, otherwise the simulation won't run because the program won't be able to recognize the starting date and the ending date. So please try to check this from the control panel in the region option, and select English USA. Let me know if you have any problems in looking this option in your machine. Okay, if you are now sure that this format option is okay in your machine. Okay, now I see a notification in the chat. Okay, perfect. This is the right format. Well done. So yeah, that's good. Okay. So now with this option, you will be able to perform the correct simulation. Okay, now let's move to the last part, the last option that must be specified in the plan, which are the computation settings. Here there are 4 time steps that must be selected by the user. These, let's start with the first one, the computation interval, which is the time step that will be used in the unsteady flow calculation. This is probably one of the most important parameters, and this computational interval, it's not always the same. It depends on several factors as velocity, cross-section shape, input you are using, the flow, any presence of structure, and many other. Let's say that in general, using small computational interval will provide more accurate computation, but at the same time, using computational interval too much small cause the model to take a lot longer to run. So you have to find somehow a balance between a computational interval which isn't too big but neither too small. In this case, we can set a computational interval of 2 minutes. Should be okay for this example. And let's see what are the other interval that must be selected. The hydrograph output interval is another time interval, and in this case, this one defines at what interval the computed stage and flow hydrograph will be written in the DSS output file, because every time you perform a simulation, the program will automatically create a DSS file in which there are all the output results saved in. So with this time interval, you set how many often the computed stage and flow must be saved in this DSS file. This interval must be equal to or larger than the computational interval you've set. In this case, let's set 1 day, because we are performing a quite long simulation. So to be able to see the stage and flow every day will be quite good. The detailed output interval is used to set how often the profiles of water surface elevation and flow will be saved, because the profiles are not written for every computational time step, because it will require too much space to store all these kind of information. And so this option allows the user to set a much larger time interval in order to have some results which are not too big. So let's set it 1 week. And then the last parameter, the mapping output interval, is actually useful when you compute b-dimensional analysis, because this is the interval at which you can visualize the mapping out in the RAS mapper view. Let's set also this one equal to 1 day, but it's more relevant when you are working with b-dimensional models. Okay, last part of this computational setting. Here you can see the position of the DSS file that will be saved after the computation. You can eventually click to select another position or set another name. And automatically the name of the DSS file will be equal to the name of the project to be easily recognized by the user. Another useful option that is available from the plan is to select in which location the program have to save the stage and the flow output. Because by default, stage and flow output will be computed and show in the output results only for the first and the last cross section, or where are located some structure, inline structures. But if you want to check the result in other cross section along the river, you have to specify which locations. So go to the option menu and select the first voice, stage and flow output location. And from here, you can, for example, select another 1, 2 cross-section position. This is just an example. You can just click, and with the arrow, you will confirm and move this cross-section in the selected location list. For example, now I add a couple of cross-section. You can decide to put one more, just to see then that the results will be given also for this cross section, and confirm. Okay, or now our plan is ready. Let's save it from the file menu. Save plan as. I give as a title Dindir Unsteady. And as a short name, I just put unsteady. Okay. Now our plan is ready, and we can compute to perform the simulation. I click compute, and let's see if everything is okay. It may take a little time, because we are simulating 2 months. But yeah, the geometry is quite small in this case, so it should not take too much. Okay, in my case, the simulation is done, it's finished correctly without any errors. I give you some times to see if the run is performing correctly also in your project. if you had any error or if you missing some data, let me know. We can see together again. I see that someone of you is writing in the chat, so I just wait a little bit to understand if there is a problem or if everything okay. Okay, Marnat is saying that he lost the track of everything. I will wait for the recording to follow the step after this. Okay, sorry. So you miss a part of the training. Okay, yes, for sure. The recording will be available. Also today in the afternoon, I will share the link with you, and you can try to do again the exercise if you lost most of the part. Does someone else manage to follow these steps and to perform the computation? Okay, I try to go on, but if you have any doubts, any error, you can feel free to stop me. Otherwise, yes, of course, the recording will be available after the session. So we have completed, let's say, a simulation. The only things we can do now is check at the results, and there are many ways we can look at them. First one is go to the hydraulic property tables. So let's close the unsteady flow editor. If you select from the main menu this hydraulic property table, you will see all the property tables that have been calculated from the geometric preprocessor. So all the property tables, the rating curves. Let's see. From here, you can move through the different cross-section. You can essentially see on the left graph, you see the water surface elevation drawn in the profile of the cross-section. You can see the graph, but you can also click on this table button, and you can see also the the table format, you can remove the graph or remove the table. Then you can see in this middle graph that plot the area and the elevation, and you see how this relation changes at the changing of flow and elevation. Also in this case, you can turn on or off the graph and the table according to which data you are interested at looking at. And also the table with all the values. Maybe it can be useful to copy it and extract these values to use in other calculation or to show the results. You can move in all the cross-section of the system. And from the option menu, you can also select other plan. If you have multiple plans, you can plot them together to compare the values, or also from the menu option, you can also decide which variable to plot. There are many other you can decide to see in the profile. So this one is the first way to see some hydraulic properties of the system. Okay, then you can also see the plot stage and the flow hydrograph by clicking this button. Here you will see, which is really useful to see what have you simulated during your unsteady flow analysis. Here in this plot, you can see the stage hydrograph and the flow hydrograph for the cross-section, the upstream, the downstream, and in this case there are two more that are the two cross-section that I checked in the output location. If you select more cross-section, you will be able to see this graph also for other cross-section. Here in this graph, now we are seeing both the flow, which is the green graph, and the stage, which is the blue curve. From here, you can turn on and turn off any of this data. And as you move to the graph, you will be able to see the specific value of the variable plotted. So it's quite useful, for example, to see that the maximum flow that has been simulated is equal to 110 cubic meter per second, more or less. Or you can turn on the table and check for the specific maximum value, which more or less here, okay, it's 110 cubic meter per second. And when we add this maximum flow, we have an elevation of 764 meters in this cross section. From the option menu, also here, you can decide to plot, you can select which one of these two variables to be plotted. Also here, you can select other plans if you have more than one. And there are also some useful summary here in this table. For each cross section, you can see the maximum stage and flow and at what time it happens. So if I move up and down with cross section, you will see the maximum stage and the maximum flow for each of this cross section. Okay, I show you how to change the variables, how to see the results both in graphical or tabular format. Another useful tool to see the results is using the profile. With the profile button, by clicking here, you will be able to see the water profile of the ridge. You can also zoom in to see a specific area. Then you can move using the shift key of the keyboard, or from the option you can select pen and move through the ridge. Can go back again to the full plot. And one interesting thing is you can see how the profile changes during the time by clicking this animate. First, the first profile you can find is the maximum one. Then if you move, you see how it evolves during the simulation. Now we set to plot the profile with a time interval of 1 week, and since we were simulating more or less 2 months, we have not so many profile, but it's enough, for example, to check that the profile changes accordingly to the flow hydrograph we set. Because here you can see from the hydrograph we started with a very low flow, then there is one peak, let's say this part, then the flow go down again, and then go to the maximum peak, and then started decreasing again. And you can see this that happen also in the simulation. We start with a very low flow, then it go up, then down. There is also this red bar that show you where are you located in while plotting the profile. So how here it's we have a low profile, and then you go up again until reaching the most highest flow, and then again go back when the flow started to decrease during the simulation. Yeah, this is important to understand if your simulation is correct. Just maybe starting from this kind of information, and this in this case it's pretty coherent. So we know that somehow we set the correct data. Also here from the profile, you can also decide to plot other variables. The default one are the water surface, the energy, the critical depth, but you can also decide to remove some of them. If you remove, for example, the fill-in water surface, you will see only the water surface line without the filled color. Or another useful things is like to add the labels with the river and ridge name. Maybe this one, the cross-section river station. See, it doesn't work. Why? Labels. River Actually, it's not working. You should add the label for each cross section. Okay, I was looking for this option. In this case, the landmarks, you will be able to check the river station of each of these cross-section along the bluff, so you can easily recognize in which location of the river you are. So this was an example of how to perform the unsteady flow analysis. If you want, you can also actually check the results from the RAS mapper. Let's have a look also from here. If you turn on the results layer, you will have a layer for the unsteady flow simulation, and inside this, you can plot, for example, the depth, turn off the other. Yeah, in this case, it's not so good, the results, because yeah, the mapping output are generally used for the bidimensional analysis, but somehow you can see also a little bit of the elevation from here. It's not so accurate because it's yeah, the mapping out results are most used for the bidimensional result, but somehow sometimes it's useful to see the results also from here. Let's go back to our geometries. Do you have any question about this unsteady flow simulation? Any curiosity? Any problem? This was a, let's say, pretty basic example about how to perform an unsteady flow simulation, but at the same time is an example that includes all the necessary steps and elements you need to set in your hydraulic model in order to perform correctly an unsteady flow analysis, and so to obtain the results in terms of stage and flow in your river system, which is the purpose of the hydraulic simulations. So just to summarize a little bit, once you have created a new project, once you have created the geometry with the data that correctly schematize your river system, you have to create the unsteady flow file, which contain both the boundary condition and both the initial condition. You can also add any optional internal location. So it's what we did using the flow hydrograph from the HMS software. This is a very important aspect to see how the HMS model output can be used as input in the RAS model. So that's the way you can connect the hydrologic model with the hydraulic model and get them somehow bonded together. in this way. The output of the hydrologic model can be used as input for this one. So once you have set all the necessary boundary condition and initial condition, the last step you will have to do to perform an unsteady flow simulation is to set the plan file where you have to set all the options for the simulation, and then you will be able to compute the unsteady flow analysis. Okay, with this, I think I'll show you most of the important things you need to know about the RAS. Of course, these are only the most important and basic information. Then there are many other options, elements, and tools, but more advanced you can use in order to improve your hydraulic model. But I think that this was a pretty complete overview of the basic elements needed to use the RAS system. If you have any question or any curiosity about what we see both today and yesterday, you can ask me. Okay, if there are not any question, I think we can end here this training. Thank you all for the participation. If maybe there is a question, Dr. Nahid is writing, so let's wait a moment.
It is not a question, practical, but I would like to thank you for your effort, despite all the technical problems that we face today. But your work is very great. Thank you very much. Thank you.
Okay, thank you very much. I hope this 2-day training was pretty clear. At least I hope, yeah, the training was good for you. Thank you to you all. And then next week you are going to attend the SWOT training, and then you are going to see also the RESIM training, which are other software really interesting and important for the hydraulic and hydrological modeling. So thank you again to everything. I will share in the afternoon also the recordings of today's session. And yeah, feel free to ask any question if you have any doubt also in the next day when you maybe look again at the recordings, and if you find any problems. So thank you and goodbye. Thank you everything again.